So if I have a circle, um, one thing we haven't talked about are chords. So if I have a line, oops, if I have a line like this that goes from one end of the circle to the other, okay, that's called a chord. Okay. And if I have another line, that's also called a chord. And what chords do is they just go from the edge of the circle to the edge of the circle. Now, technically, a diameter is a chord, but it goes through the center of the circle. Now, if I label this as A, and I label this as D, and I label this as the point B and the point C, and I'm gonna, in the textbook, it doesn't draw these big points, but I'm gonna draw them so you guys can kind of hone in on what I'm talking about. One of the theorems is that if AB is congruent to CD, in other words, if I have AB is congruent to CD, then AB and CD are congruent. So the line segment AB is congruent to CD. Okay? So that's just one theorem that we'll be talking about. And then another theorem that we're going to be talking about is the perpendicular chord theorem. So this one has a name. It's just the congruent corresponding chord theorem. Congruent corresponding chord theorem. But the other one, and this is in the printable notes, so you could look at the printable notes which are on my website. The next one is the perpendicular perpendicular chord bisector theorem. Okay. So now what that looks like is if I have a circle like this and I have a diameter, which is a chord technically, and let's label this as E, let's label this as G, and then I have, if the diameter bisects a chord, okay, such that it is perpendicular to that chord. In other words, if I have the chord FD, I'll write this out a little more formally. FDH. Then it bisects the chord. Okay, and the arc lengths are corresponding. So let me write down this theorem first. So if EG is the diameter and EG is perpendicular to DF. Remember, this little thing right here means perpendicular. Okay. If that's perpendicular, then HD is congruent to HF. In other words, this is congruent to this. Okay. And GD, the arc of GD is congruent to the arc of GF. So this then is congruent to this. Okay? And then the converse of that is just going the opposite way, which is saying that if EG is a perpendicular is a perpendicular bisector of the chord FD, then EG is a diameter. Okay. So that was all the theorems we need to do this next example problem. So what we'll do is let's just go ahead and do it. So let me turn the page here. So that means that if I have a circle that looks like this, and I have a point P here, and I have a chord like this that says GF, and then I have another one like this where I have JK, and the point O, and I'm told that this arc is 80 degrees. In other words, let's label what we're looking at. We're looking at the circle P is congruent to, this is what they're telling us, and this is a Q, not an O, circle Q. In other words, they have the same radius. That's how you can tell. So we don't talk about it because it's so easy, but like congruent circles, same radius. So because this radius is congruent to this radius, they're congruent circles. So that's pretty easy to prove congruent circles. But we're told that they're congruent, and FG is equal to or congruent to JK. We know that just because we have an arc here and one little hash mark there, and then the measure of JK, the arc length JK, is also congruent to the measure of FG. Then it says find the measure of FG, the arc. So what they're saying is we had an example problem yesterday where the central angles were congruent, but because there were different size circles, in other words, they had different radiuses, the arc lengths were not the same length, but the measures of the angle were the same. So, but these are the same circles; they have the same radius. So basically, this is congruent to this. So that's congruent to the measure of JK, which is equal to 80 degrees. That's it. That's example 1.